case number 1, very fine fault and cross-well connectivity. So here we are with 5 producing wells. One of them is horizontal. No, 2 of them are horizontal, sorry. All of them are producers, and there is a probable fault just between this group of the wells. You can see it in dotted line, right? So we have the PDG history on the producer OP1. So let's see what data we have. Here's the bottom hole pressure in blue in the panel above, and you can see several panels of rates. So these are the rates and GOR of these 5 wells. So this is in fact all the data that we need inside MRT to build this mathematical model of this interfering block. So let's go to the results. So I don't want to go deep into the procedure, because I think it would be, you know, a topic for completely another webinar. But now let's just, you know, look through the cases and see what we can actually get from this technology. So first of all, we reconstructed the formation pressure history for this oil producer number 1. Yeah, you can see that the pressure has been declining. Of course, it's declining because it's, you know, naturally depleted reservoir. And we can see also the history of a pressure drawdown. You see it was high in the beginning, and then lately it's been decreasing along with the rates, right? Okay. Also, we can build some prediction of formation pressure, and we can see that if we keep the current rates of all these 5 wells, we will see additional, well, slight additional decline in nearest month, right? Another thing we can deliver is the productivity index, because now, as we can reconstruct the whole history of formation pressure, and we also have the BHP, and we also have the rate, we can just calculate the productivity index, and I plot it here in yellow points in the top panel, and you can see that the productivity index has been relatively stable. Well, there's no issue with the well. We don't see that the contact is getting any worse, so it's actually fine. Another thing we can deliver is IPR. So now, as we have the whole history of formation pressure, we can build several IPR curves for any given formation pressure, and we can build a model, for example a Vogel model right here, to fit all this data that we see, and then we can actually try to predict what would be our IPR later on as we deplete the reservoir even more. Right, so on this plot you can see the theoretical Vogel curves, which we tried to fit on these colored points, which are in fact rates with the different formation pressures. Right. Now, another thing that we can give is the estimation of reservoir and well properties. Because as we get this drawdown transient response, we can plot it on a log-log plot. These are 2 black dotted lines here, and they will represent the model of the well and reservoir. So now I just compare it to these colored dots, which are one of the build-ups in the history of this well. So now you can see that somewhere around radial flow, the MRT response actually fits the PBU, but we have the long and smooth history, and we can build a sufficient model given the precise estimation of reservoir properties, reservoir geometry, and we can of course quantify it with the numbers here. All right, and the same thing we can do with the cross-well transient responses. So what is a cross-well transient response? Again, if we produce in well number 1, what would be the pressure response in well number 2, right? So this is actually a kind of a very simple pressure interference test. So I can just interpret this data, for example, like here on this log-log plot. I can plot it on the log-log plot, see the radial flow, and then estimate the transmissibility. And that would be the cross-well transmissibility in average. And then another thing we can get is the decomposition of the pressure impact. So our well is no doubt under impact of surrounding wells, but now we can just quantify the impact of every well. So what we can see on this plot is that we see the impact of producers number 2 and 3, but we don't see any impact from producers number 4 and 5. So if we go back on the map, you will see that these 2 wells behind this fault, because of insufficient history of these wells, and what I mean here is in order for this technology to work, every well needs to have some history of events in the rate sequence. So if your well has been producing stable ever since it's been launched, it would be very hard to say if it's impacting another well or not, right? Because the pressure would just smoothly fall down, and you know, it could be due to reservoir boundaries, or it could be the impact of these wells. And there is no technology in the world which could actually say which is which, right? But in this case, both of these wells, they have very sharp events in the history, and as we don't see any impact, we are quite certain to say that this fault is impermeable after all. So that's the story. And additionally, there is another finding. So we estimated the transmissibility around the well itself, and then we estimated the cross-well transmissibilities between these 2 wells and these 2 wells. And you can see that the values are quite close. So it seems like the reservoir is quite nice, and the sweep, aerial sweep, vertical sweep here is actually quite nice. So maybe these reservoirs could be considered a nice target for a water flood. But again, now that we are certain that we have this impermeable fault here, then the strategy of the water flood would, of course, be changing, right? Because we cannot create a sufficient water flood system here with just one injection well, unfortunately. All right, now let's go to case number 4. Justifying well spacing. So here we are in a big oil field, giant amount of reserves actually, and it's all been drilled with horizontal wells. This is only a small part of the field actually. Yeah, by the way, this is an SPE paper. You can see more of this in this SPE paper. And the regulator, the government regulator, is asking the oil company, are you sure that your well spacing is close enough? Are you sure you do not need to drill infills now? And one of the means to understand the how close for now is the well spacing is to understand the cross-well interference. So we had several wells here with the long bottom hole pressure history, which were used as focus wells for MRT. So let's see the results. So after we performed the MRT, we had 2 histories of formation pressure around each well. You can see that this particular well, number 6, has the deepest pressure decline and the highest depletion. As a matter of fact, it has the lowest transmissibility in this area, so it probably is just a local thing. But again, it seems like all these wells are connected, and they are connected to the offset wells, and we see some pressure interference. But for now, as we don't have yet any water flood, any water injection, our prediction of formation pressure is a further decline, of course, right? And then here on these 4 plots, you can see the cross-well impact. So the colored lines on all of each of this plot are showing the individual pressure impact of wells surrounding these focus wells. And what we can derive from these plots is that the cumulative impact of offset wells for almost each of these wells is actually higher than the impact of the well itself. So most of the depletion now is caused by offset wells. So qualitatively, it tells us that the well spacing is quite sufficient, because we have a serious decline in the wells due to offset wells production. Also, along with these results, we try to identify the wells which would be nice for converting to injection, because the client is actually considering emerging the water flood in this field, and we can see that some wells have quite high pressure impact, and sometimes it's caused by low connected thickness between the wells. So each of these wells would not be such a good candidate for conversion, because it would be quite soon flooding the other well, and we would have the early water breakthrough in this pair of the wells, right? Also, we would see some wells with a very low pressure impact, and sometimes it would mean some kind of a baffle between the wells. And again, in this direction, the water flood would not go as efficiently, right? But we can still see a couple of wells on this field which we think are nice candidates for to be converted to injection. One of them is right here in the center, and another one, let me see. Yeah, as a matter of fact, here is another one. So these two wells, this well outside the area and this well right in this middle of it, are nice candidates for converting into injectors. So this is another type of recommendation that we can get from just analyzing the history of bottom hole pressure and rates on the well. And another thing we saw here is that there was a drop in the productivity index for each of those wells. So as our reservoir pressure is going down, and it again crossed the line of bubble points, unfortunately we have more and more gas around the well in the reservoir, and unfortunately it leads to decline in productivity index. And for some wells the decline is quite sharp. You can see that for well 4, for example, the productivity index is twice less than the initial one.